Okay, hello. The tutorial for week 6. Okay, we can start with the first problem. Here, the telescopian link is hinged at O and its end A is given a constant upward velocity of 2 meters per second by the piston rod of the fixed hydraulic cylinder B. Calculate the angular velocity and the angular acceleration of link OA for the instant when y is equal to 1 meter. Here there is two different methods. You can use two different methods at least. First is using the velocity equation for point A with respect to point A. I mean, you can write the velocity of A, and you know that the velocity of A, because this cylinder is rotating about point O with angular velocity theta and angular acceleration theta dot theta dot and theta double dot. So you can write that the velocity of A is equal to r times by omega, or in vector form it will be omega cross r, and omega is theta dot. And in this coordinate system, you know that when A is going up, the omega or theta dot will be in negative direction of z. So you can write and find omega from this equation, because you know how much is the velocity of A. And also for the acceleration, you know that the acceleration of point A is omega cross r plus alpha cross r, and then you can calculate the alpha. But the second method that I used here is using the geometry and the relation between the edges in triangle OAB. For this purpose, we can write the position of A and show it with RA, which is equal to y times by j. Here you can see in this coordinate system, we have a coordinate system which its origin located here at point B. So the velocity of A is equal to y dot j, which at this time is 2j. Here you can see the velocity of point A is in upward direction and it's a constant velocity. So it will be 2 meter per second in upward direction and it's 2j. And now you can look at the triangle OAB. In this triangle, length AB is equal to 1 meter at this instance. OB is 0.5 and it's a constant value. And OA, which we don't need it, but we can write the relation for this angle theta. So tangent theta is equal to y divided by half. And from here you can write that y is equal to half times by tangent theta. So if you find the derivative of y, it will be with dy to dt, or y dot is equal to half times by the derivative of tangent theta with respect to time. You know that theta is a function of time, so the derivative of tangent theta is theta dot times by the derivative of tangent, which is secant squared. Okay, so here you can see this is the formula. The next step, if you use the equation 1 and equation 2, you can conclude that theta dot, which is the angular velocity of the OA, is equal to 2 divided by half times by secant squared of theta. To find the theta at this instant, you can easily find it, because we know that at this instant y is equal to 1 and OB is equal to half, so theta is equal to 63.4, because theta is tangent inverse of 1 divided by half. So theta dot at this instance will be calculated. For the acceleration, you need to find the y double dot, or second derivative of y with respect to time, and we know that this term is equal to 0, because here, based on the problem, this is a constant velocity for point A. So the acceleration of point A, which is y double dot, it must be equal to 0. So from here you can substitute and calculate the second derivative of y with respect to time. Here you calculated the y dot, so you can calculate the second derivative by finding the derivative of this term. The derivative of this term is the derivative of theta dot with respect to time times by second square plus the derivative of second square with respect to time times by theta dot. And if you calculate and simplify, you can extract this term. It must be equal to 0, and from here you can easily obtain the theta double dot or the angular acceleration, and it's equal to minus 2.56. This is the geometry relation, as I told you. Also, you can use the vector equations and vector relations calculations to find the angular velocity, angular acceleration. Okay. The second problem here, we have the pin in the rotating arm OA engage the slotted link and causes it to rotate. Show that the angular velocity of CB, this link, is 1/2 that of OA regardless of the angle theta. So we need to find the relation between this angular velocity. We know that angular velocity of OA is omega OA. So at this moment we can assume that pin here in this pin, which we call it P, point P, is a point on link OA, and P prime is a point on CB, and P prime is coincident with P. So if you look at the triangle and use the relation between VP and VP prime, you can easily write that VP prime is equal to VP times by cosine theta, which theta is this angle. Okay, so here, or you can use the geometry of the vectors and find the relation between VP and VP prime. So on the other hand, we know that VP is B times by omega OA, because P is imaginary point on link OA and P prime is an imaginary point on link BC. So the velocity of VP is equal to omega OA times by B, and the velocity of a point at on the link CB, which we call it VP prime, is R, the length, times by omega BC. And also in this triangle, if you look at this triangle CPO, here I plotted this, we have these two lengths are equal to B, and if we call it R, you can easily find that R is equal to 2B times by cosine theta. Now you can substitute into these equations. Instead of R, if you substitute 2 times by B times by cosine theta, and then substitute into this equation relation between VP prime and VP, you can easily calculate that omega BC is equal to omega OA divided by 2, or 2 times by omega BC is equal to omega OA. So we can conclude that the angular velocity of link BC is related to omega OA, and it's not depend on the theta. Okay, so this is the solution for the second equation. Second problem. Okay, and the last one, which is the third problem. Here we have a 4-bar linkage which is controlled with link OA, has a counterclockwise angular velocity omega 0, which is 10 radian per second, during a short interval of motion. And we want to, when the link CB passes the vertical position shown, point A has a coordinates minus 60 and 80. Of course, with respect to this coordinate system, this is X and Y axis. So in this coordinate system, at this moment, the coordinates of A is minus 60 and 80. By means of vector algebra, determine the angular velocities of A, B, and BC. Again, here we have solved a lot of problems like this. It's pretty simple. We know the velocity of B direction, and also we know the velocity of A completely, the direction and the amplitude. Also, we know that the angular velocity of link OA, and we need to calculate the angular velocity of link BC and AB. using the velocity equation for point B, because point B is located on link AB and BC, and we can find the direction of the velocity of B because it has a pure rotational motion about C. But if you look at point B in link AB, it will have a general motion. So you can write the relative velocity equation between point B and A. So first we can write the velocity of A, which is omega OA cross ROA. In this coordinate system, easily you can find that ROA is minus 60 or minus 0.06 I plus 80 millimeter or 0.08 J. So this is ROA, and omega OA according to this coordinate system is 10K. So you can substitute and find the velocity of A using a cross product calculation. This is the velocity of A. The velocity of B, if you look at in link BC, it has a pure rotational motion, so similar to the velocity of A. It's equal to omega BC cross RBC. RBC is at this moment is 0.18 because this length, the length of link BC is 0.18 or 180 millimeter, so it will be 0.18 J, and omega BC cross RBC will be equal to minus 0.18 omega BCI, because if we assume that omega BC in vector form is in positive direction of K, it will be K cross J, and it's equal to I with a negative sign. So this is VB. And finally, in the link AB, you can write the velocity of B with respect to the velocity of A plus omega AB cross RB with respect to A. Here, the coordinate system, you can use a translational coordinate system. Link AB is a rigid body, so you can write the velocity of point B with respect to point A. And here you only need to calculate RB with respect to A. And if you look at here, RB with respect to A, it means that you can move this coordinate system from point O to point A, and when you put the coordinate system on point A, you can easily calculate the position vector of B with respect to A, which is equal to the x component is this length, and it's equal to 180 plus 60, and the y component is 180 minus 80. So you can easily find RB with respect to A and substitute into the equation, and finally you will have one vector equation, which is in fact two algebraic equations, one the coefficient of I and the other one the coefficient of J, and then you can calculate omega AB and omega BC by solving these two equations. So this is the solution for the last problem, and I will upload this file on the Moodle, and you can refer to this file, and if you have any question you can send an email to me, or you can ask me in Viber. Okay, thank you and bye.